This course is a continuation of EELE 261 Introduction to Logic Circuits, or an equivalent course. In this prior course, you should have gained experience with working with binary number systems, combinational logic design, and sequential logic design, and had an introduction to a hardware description language. This is the second part in this sequence of logic design courses where we go a little bit more higher in abstraction and only use a hardware description language in order to build larger digital systems. So what you should have coming into this class, whether you took 261 or an equivalent class, is the following. So in 261, we started with just looking at the basics of analog versus digital, where we learned that an analog system uses real information that is coded continuously, or that is continuous representation of the information, whereas digital is a coded representation. And the codes that we used were typically binary codes. So then we learned about the number systems. Okay, so we learned about instead of using decimal to represent information as a number, we learned the binary number system, and that was because computers are built with basically switches. Okay, so a switch can either be on or off, and that can produce two discrete voltage levels. And what we do is we use those voltage levels to represent a number, 1 or a 0. And then we combine those to create larger and larger numbers, which represents more complex information, and that's how information is acted upon within a computer. Within number systems, we looked at things like representing groups of ones and zeros using the hexadecimal number system. We looked at basic binary arithmetic, such as addition and subtraction, and then we looked at representing negative numbers using 2's complement. You should also remember Module 3, which was on digital circuitry and interfacing. This is where we looked at the basic logic operations, things like ands and ors and nands and nors and inverts, and we looked at their truth tables and how they produced an output based upon inputs, but it was all a logic value. And what we mean by logic value is that the inputs to a digital circuit are going to be either a 0 or a 1, and then the circuit is going to compute the output, which will also be a 0 and 1. So when we think about a logic gate, that's the basic operations that can take place on ones and zeros and produce an output. But we wanted to actually build hardware. So we needed to look at how do you create these basic gates in the real world. And so we actually looked at discrete parts from the 74HC series, and we were able to put these parts down on our breadboard and actually build basic logic circuits. Now, when we started building real circuits, we had to consider the real implementation of these circuits. So we had to consider things like power supplies and grounds. So these logic gates, they don't work unless you provide them a VCC voltage and also a ground. And we also needed to look at the interfacing between gates. So if one gate is going to produce a logic 1 and it's represented as a certain voltage level, the gate that receives that information has to be able to interpret that voltage level as the logic 1. So we needed to be able to design circuits that can interface with each other, and we needed to be able to understand the operation of these gates in order to interface them properly. So we needed to look at their data sheets. So we looked through their data sheets and we looked at a whole bunch of characteristics about these parts, and we also looked at both DC characteristics but also the AC characteristics, so how fast they switch. So once we had all these basic gates in hardware and knew how to interface them, we started looking at combinational logic design. So combinational logic design is where you build circuits that produce a logic output, and it's usually just one bit based upon multiple inputs, so 2 inputs or more, but they were more complex than a basic gate. So instead of an AND gate that had 2 inputs, you might build a circuit that could implement any arbitrary truth table, 3 input, 4 input, 5 input truth table, and we learned about how you actually synthesize the circuitry to produce the desired output. Within Module 4, we also looked at minimization. So we looked at how you can build a logic circuit to produce an output in many different forms. There are a variety of different topologies that you can use to produce the same output. So depending on what you're trying to do, you might want to choose one topology over another. So that was Module 4. So if you thinking back to Module 4, you think about things like the canonical sum of products, the canonical product of sums, a minimized sum of products using a Carnot map, or a minimized product of sums with using a Carnot map. And so that was what Module 4 was about. Then we turned our attention to the modern digital design flow, and we started looking at hardware description languages. And in the prior class that feeds into this class, we looked at VHDL as the primary mechanism to design these digital systems. VHDL is a language, and it gives us the ability to describe a logic circuit in a language. So we actually type out the functionality of the circuit, including the inputs and the outputs, how the logic is going to operate. And it was very powerful because it gave us the ability to simulate the result and make sure that the circuit is described properly before we actually build the circuit. Then the real power of the modern digital design flow is that once you have the VHDL that's accurate, you can use an automated tool to actually synthesize the circuitry for you. And so we learned how to synthesize our VHDL and create essentially a bit stream or a netlist that could be implemented on a programmable logic device. So we used an FPGA before in the prior class, and it was very powerful because we could immediately start building very large digital systems using VHDL, and we allowed the tool to create the logic for us, and that allowed us to design at a higher level of abstraction. And then we moved on to MSI logic, which is just looking at some basic combinational logic circuits, so things like encoders, decoders, multiplexers. And it was just to get a taste of, okay, there are combinational logic circuits that are so common, there's no need for everybody to design them. So what we'll do is we'll have them be designed for us, and then we'll just purchase them or use them. And we just looked at some common ones, but more importantly, we looked at how you could use the classical digital design approach to actually build them yourself. So if somebody said build a multiplexer, all you really need to know is how a multiplexer is supposed to work, create the truth table, and then synthesize the logic using a kernel map. Or you could, if you knew how it worked, you could describe the multiplexer in VHDL and synthesize it using an automated CAD tool. Finally, we wrapped up with sequential logic. This is where we started looking at circuits that could create their outputs based upon both the current value of the inputs and also the past values. So whenever you're talking about past values of something, you're implying that you need storage. So a sequential logic is circuitry that has some sort of storage mechanism. Storage is not, in this context, memory arrays, so things like DRAM in your computer. What we used was a D flip-flop. So a D flip-flop was a very fast storage device that could store 1 bit at a time, and it would only grab the input and store it upon a triggering event. And the triggering event that we used was the rising edge of a clock. So you should have all of that knowledge in your past, or you should at least know what I'm talking about roughly before taking this class. And so now we turn our attention to, what is this class about? What is logic design about? Well, for this course, what we are going to do is we're going to continue using the same textbook. And really what we're going to do is, in 261 we covered chapters 1 through 7. In this class we're going to cover chapters 8 through 13. This class is heavy in VHDL. So every lab is going to be done in VHDL. Almost all of the homeworks are going to be done in VHDL. All of the labs are going to use an FPGA board, and we're going to get to the point where everything will come together and we'll build a full computer system. So what to expect in this course, before we get into the individual content, is it is a fully online course. Okay, so you're going to be, instead of a lecture, you're going to be watching videos that I created for you. You're going to be doing homework in the form of either multiple choice quizzes within our Brightspace learning environment, or you're going to be doing VHDL simulations and uploading screenshots. You have the textbook, of course. Video and the textbook match exactly. So you can read if you prefer that, or you can watch videos if you prefer that, or you can do both to get kind of a different perspective. But keep in mind, I wrote the textbook and I did the videos, so it's kind of me describing the information in just 2 different modes. For the labs, you are only going to use VHDL, and you're only going to use the FPGA and the analog discovery. So you don't need to use any discrete parts or your breadboard. You're just going to be doing a whole ton of VHDL. So that's where we are going. So let's take a look at the topics that we're going to cover. So we're covering chapters 8 through 13. What we're going to do is we're going to start off with what we call VHDL Part 2. So coming into this, you should have been able to create a very basic combinational logic circuit using VHDL. So you should understand things like what an entity is, what an architecture is. Do some simple signal assignments with some logical operators. So you can create a 3-input AND gate, or you can create a very simple sum of products form combinational logic circuit. Once we get to this class, what we want to start doing is looking at the rest of the functionality in VHDL. So this is where we're going to start looking at how do you model events that are triggered. Okay, so instead of being continuously assigned to the output like a combinational logic circuit, how do you create a D flip-flop, or how do you create a finite state machine? So we begin looking at more advanced techniques to model behavior, such as using a process and how to trigger the process and do sequential signal assignments. So the first module we cover is just looking at the rest of the functionality within VHDL so that you can model all of the types of digital logic circuits that we see in modern digital systems. The next module is where we just get some practice doing it. So we learn all the constructs of VHDL, then what we do is let's just start looking at the most common circuits that you have. So we look at things like building a combinational logic circuit using an if-then statement or a case statement. How do you create a D flip-flop model? How do you create a finite state machine? How do you create a counter? How do you do register transfer level? So we look at the most common things that you need to design in digital logic, and we just do examples of it. Then what we do is we turn our attention to memory systems. So if you're going to build a computer someday, you need a large array of storage that's not a D flip-flop. Okay, so with D flip-flop is something we store information for, like a register or a finite state machine. But memory systems are different. Memory systems are where you have gigabytes of information that is stored in a different technology. So we need to, since we're going to have that logic functionality, we need to know how to model it in VHDL. So we look at some common technologies used to implement semiconductor memory systems. Then we look at the VHDL to model them. Then we get into programmable logic, just a short module that just looks at the common technologies that we use to implement some of these digital systems when we're prototyping, and sometimes just the final product. But we cover programmable logic because that's what we use in the lab. So we finally get to the point where we know enough about what we're trying to model that we're ready to look inside of the FPGA and figure out what they actually put on there. So once we look at this module, it's kind of neat because you actually, as you look at all the programmable little blocks inside of it, you'll understand what they do and how to actually build them. So then we finally wrap it up with looking at arithmetic circuits, and this is going to be more complex circuits, so things like adders and subtractors and multipliers and divides. And once we get through module 12, you get to the end and you will realize that you have put together all of the information needed in order to build a computer system. So you're going to be able to build the CPU of a computer system, the registers, the data routing in between it, the finite state machine that controls the execution of instructions. You're going to be able to build the memory system that can store read-only memory or read-only information. You're going to be able to model the memory that stores, volatile memory, so things like read-write memory. You're going to be able to model output registers. And we look at all of these different things that we've covered and you put them all together in the most common digital logic system that there is, which is a computer. So this course culminates with actually designing a complete 8-bit computer that is in VHDL. You're going to simulate it using a simulator. You're going to synthesize it using an automated CAD tool, and you're going to put the whole thing on an FPGA and run programs. So it's going to be kind of a culmination of the entire course. Before we get to the course logistics, let me give you a very brief background on myself, just because I'm going to be the person that you hear and see in the videos, and also I'm the person that wrote the textbook. So, and also I'm teaching the course, so sometimes it's good to know who is at the other end of this class. So, again, my name is Brock Lemire. You can call me Brock. I've been a professor at Montana State University for 12 years now. I got my bachelor's degree from MSU back in '98. I then went to work as a hardware design engineer for Hewlett Packard in Colorado. And what I did there was I designed basically digital systems. They were acquisition systems for electronic test equipment, so logic analyzers. And so what I did was a lot of FPGA design work, a lot of printed circuit board design, a lot of just digital logic design. So I did this in my past life. And I worked for Hewlett Packard for 8 years while I chipped away at getting my master's and my PhD at the University of Colorado. So I got my PhD from the University of Colorado in 2005, and I ended up coming back to Montana State in 2006 and joined the faculty in the electrical and computer engineering department. So since coming back, what I've mainly focused my research interests in, or my research area, has been on digital systems. So, digital systems are everywhere. But what I've been doing technically is I've been looking at creating reconfigurable computing systems, all FPGA based, to optimize the computer for a particular application. And what I've been doing is I've been doing a lot of work for NASA recently where I've been building these space computers for various applications, and this has allowed me to kind of stay up to tune or up to date with what is actually being used in the real world. And also we've been doing some exciting things where students that work for me have been able to build, real hardware that has been flown in space. So we have a computer right now as I speak that's on the International Space Station getting ready to be put into orbit. We just had a computer that was up there for a year where we tested how well it performed under bombardment by radiation. So this is the type of stuff that I do for my research. I also am the director of the Montana Engineering Education Research Center, and what we do there is we look at how can we improve engineering education. So engineering education it's a difficult thing, right? I mean, you have a whole bunch of knowledge that you have to bring together to perform engineering. So you need math, you need science, you need writing, you need communication, you need problem solving skills. We put that all together and we form an engineer, okay? So it's not trivial, and it's becoming more and more complex because there's just so much more information available. The systems that we build are so complex that we just need to think about new ways to try to educate people. So I've been the director of that for 3 years now, and I've received numerous grants from the National Science Foundation to kind of conduct studies on how to improve engineering education, and I do a lot of it with MSU students. So that is me. Now let's take a look at the course logistics so you can actually get started on the class. Okay, so this online class is going to be administered through our Brightspace learning environment. Okay, so the address for this is ecat.montana.edu, and it'll redirect you a little bit to this ecat1, but anyway, just ecat.montana.edu. And you log into this using your NetID and password. And once you do that, if you have any problems with logging in, you're going to want to call this 994-3255 number, and they'll help you get in there. Once you log in, what you're going to see is all of your active courses. And mine is going to look a tiny bit different than yours because I'm the instructor, but I've got my course down here. I'm going to come down to Logic Design, and this is what you'll see when you enter the course. So you'll see this banner and it says Logic Design, it lets you know you're in the right place. Along the top of Brightspace, you're going to see all these different tools, but what I've done with this course is I've linked everything in content. So you really should only ever have to go into content if you want to find access to everything. So I've linked all the assignments and quizzes and stuff like that, but content is where you find the content. Okay, so when you come in here, I put an announcement that just says welcome, just as a landing pad so you know you're in the right course. So this is where you come. Now let's go to content right now and take a look at the course. Okay, so when I come into here, what I'm going to see is I'm going to see this one folder called EELE 367 course activities. Okay, so if I click on that, what I'm going to see is I'm going to come down here and I see all of these different activities we're going to do. Notice that there's a page for every module. Okay, so you're going to see module 8, VHDL part 2. On these pages is the links to everything. Okay, so this is the links to the reading assignments, what you're going to be doing, the videos, the homework, where to upload your homework, where to take the quizzes, etc., etc. Okay, so you just click on these and just work all your way through them. If I start off with course information and syllabus, what you're going to see here is just a brief overview of the course that is the stuff in the syllabus, but this is where you would find links to stuff like my email. So when you come in here, you're going to see the course syllabus. You obviously have found the course overview video, but let's take a look at the course syllabus first before we start flipping through the pages of the course. All right, so here's the course syllabus and description of the course. So we already kind of covered that. This is the part 2 of a course. Outcomes, we already covered that. You already know me. Here's the link to my email. But we also have a teaching assistant for this. So, this is an accelerated class, so you're going to want to have rapid feedback. So we actually have Trevor Gall, who is going to be helping out this summer, and his email is right here, tgall7@gmail.com. So when you email for help, you should always email both of us, and the first one of us will reply as soon as we can, okay? All right, here's the big one. This is a 4-week summer session course. Now, this is an accelerated format, and a semester-based course is going to be done in 4 weeks. So you're essentially every day that you engage in the course is like a whole week's worth of learning. Now, that is critical because it's important that you know that this is an accelerated course. This is not a short course. This is a full semester-based course that we're going to do in 4 weeks. That means it's going to be nearly impossible if you're trying to work a full-time job, or it's going to be impossible if you're going to take a week off during it, because that would be like missing a month of school during the spring semester. So you got to make sure that if you take this course, this is your number one priority, and you be prepared of how much time it's going to take. The good thing is that it's over in 4 weeks. And it also is fully online. So that means you don't have to be on the MSU campus to take this course. Everything can be done remotely. The course is designed so you can do this from anywhere on the planet, as long as you have the following 4 things. You need a computer with internet connection running Windows. Now that's critical. The software we're going to use does not run on a Mac, okay? So you got to have a Windows machine. You could do it with a Linux machine, but I'm assuming everybody has Windows. You can't do it with a Mac, just flat out. The software we use called Quartus, that has the model sim simulation software and the synthesis tools, it doesn't run on a Mac, so there's no way to do this course without it. You have to have access to a Windows machine. The second thing you need is the textbook. So this is the same textbook from 261, written by me, Introduction to Logic Circuits with Logic Design, and Logic Design with VHDL. And Amazon usually has the cheapest hardcover version, so I usually see them for about $60 brand new. You need to have the Digital Logic Portable Lab Kit. The lab kit, if you took 261 and you still have the kit, you just keep it and continue into this course. The kit has the FPGA board, and it has the Analog Discovery portable instrument that you'll see. It also has a bunch of discrete components and a breadboard. In this class, we're only going to use the FPGA board and the Analog Discovery. So if you're taking this class and you didn't just take 261 this summer, I'll ship you a kit, and so by the time you read this video, I will already have sent it to you. Okay, and then you need a camera capable of taking short videos. The way we're going to do lab demos is you're going to actually take videos of them and upload them to Brightspace. You're going to need a little camera that'll do that. Almost always it's just a cell phone or a smartphone, okay? And then we're going to be doing screenshots of like measurements and so, but the main way that you're going to demo is to take a short video, okay? All right, so then as we go through the syllabus, prerequisite, you have to have had this 200 level Introduction to Logic Circuits class. You need to have already designed a combination of logic circuit using a K-map. You need to know what a sum of products is. You need to know what a finite state machine is and know how to design it. But you also need to have experience or a little bit of experience with VHDL or a hardware description language. If you took a class that used another language like Verilog, that's fine. You just need to have used that. Because this class is so heavily based in VHDL, there's just not enough time for you to learn it from scratch and also engage in the assignments. We assume that you're ready to hit the ground on day one, so we don't review. We just jump right in and we start coding. Okay, course website, I already showed you how to log in. Again, if you have any difficulties with your password, just call 994-3255. In terms of office hours and lab demos, we really don't have any because we're always on. So the primary mode of communication for this class is email. If you get stuck on anything, email me and Trevor, and we'll reply as soon as we can. I would say guaranteed within 24 hours, but realistically, we're going to reply within a couple hours. Assuming that you don't email in the middle of the night, okay? So we're not going to be replying at 2 a.m. if you're working during that, but during normal hours, we'll get back to you really quickly. Okay, the grading distribution for the class is there's going to be homework, labs, end of module quizzes, and a final project. The homework is worth 150 points or 15% of the grade. And when you go in and look at your grade, you're going to see that there's 1,000 points available. So the homework is going to be primarily VHDL simulation using model sim, but there's also going to be some multiple choice format questions. The labs are worth 45% of your score. That's because the labs is where all the learning comes from. Every module is going to have an end-of-module quiz, which is a multiple-choice format quiz, which kind of summarizes what you just learned. So there's going to be, module 8, 9, 10, 11, 12. So there's 5 end-of-module quizzes. And then you have a final project. The final project is going to be to design and implement a full computer system in VHDL and put it on the FPGA. If you think about it, you've got 20% is a computer, 45% is the labs, 65% of this class is just VHDL. So you are going to be building large digital systems using a hardware description language and implementing them. So that's where the vast majority of the learning comes from, is actually building these systems. Of the homework, over half of it is VHDL. So you're talking about like 3/4 of this class is VHDL. So be prepared to do some typing. All right, grading, I usually just grade straight. 90% is an A, 80 is a B, 70 is a C. I usually don't get pluses and minuses unless it's extraordinary circumstances. So you're guaranteed, though, if you get a 90.0001%, you will get an A. Okay, don't worry about an A minus. Okay, but you have to pass the lab. Okay, you got to get at least a 70% in the lab in order to pass the class. Okay, that's because all the learning takes place in the lab. You can't just plunk through the multiple choice homework problems and guess and get those somewhat right and pass the class. All the learning takes place when you build these circuits. Okay, academic policies. You can work with other classmates if you want. You just have to make sure that you turn in your own work. Everybody turns in work. Okay, so even if you're partnered up with somebody and you only have one set of files to turn in for the lab, that's fine. Just make sure to upload it to your own Dropbox so we can grade it. What the academic policy is about is don't turn in somebody else's work that you didn't do. Okay, there's a big difference between working with somebody where you're both collaborating at one computer and you generate one design file versus somebody did the problem for you and gave you the design file and you uploaded it. Okay, so it's common sense, don't cheat. All right, course components. How are you going to learn all this stuff? Number one, we have reading assignments and instructional videos. So this is the way that the information is given to you, okay? We cover chapters 8 through 13 in the textbook. We follow the textbook exactly. So you should be able to just open the book up to chapter 8 and start working through it, and we're going to follow. We're going to do every section in the book all the way until the end. Every one of the sections in the book has one or more instructional videos. They're all on YouTube, so they follow exactly. It's just me and both of them. So whatever mode you like to use, it's there for you. Then the way that you get practice with the material is through homework. Now homework is graded, and there's going to be daily homework assignment, and I'll look at the deadlines here in a second, but every day you're going to be doing some sort of homework, okay? Then there's the laboratory. This is also graded. Almost every day or every 2 days you're going to have a lab, and you're going to demo this using short videos that you upload. Then of course you got the end of module quizzes. Now the end of module quizzes, the reason that they're a little bit different from like the homework, even though you might use the same format, they're multiple choice format, the quizzes are timed. So they're to emulate what it would be like if you sat down in a live class and somebody handed out a piece of paper and said go. So you got to have the information in your head. There's not going to be enough time for you to actually scroll through the book and find the answer. You need to study and prepare for these. So they're going to be anywhere between 30 minutes to 90 minutes, depending on the module. But once you hit go, the clock starts and then it ends and then you're done. Homework is not like that. If it's a multiple choice homework, you can open it up at the beginning of the class, look at it, you can enter your information, you can save, and then come back later. The only deadline is the actual deadline for the homework. Okay, and then there's the final project. This is a big one. I have a big video of this later in the class that you'll watch, but you're gonna just do a whole bunch of really cool stuff to build this full computer. All right, here it is. This is the schedule. That you have 4 weeks. Every day, the class is broken out as if you were meeting Monday, Tuesday, Thursday, Friday. Okay. On every one of these days, there's going to be a lot of activity associated with it. If you think about a 16-week semester or a 15-week semester, the expectation for a class in terms of workload is a 4-credit class, or every credit that you take is supposed to be approximately 2 to 3 hours of work. So that means, for this class, let's just use 2 hours of work. So if you take a 1-credit class, that's 2 hours per week that you work on it in a normal semester. So if you took 15 credits, if you think about that, that's somewhere between, 30 to, what would that be? 30 to 45 hours of effort. So yeah, if you take a 15-credit load, you are essentially a full-time employee. Comes out to be about 40 hours on average of how much time you're spending. That's right. That's exactly what it is. That's why 15 credits is considered a full-time job. Okay, so now let's apply that to this class. So you have this class right here is 4 credits. So you should be spending, in a normal semester, a 4-month semester, you're going to be spending 4 times 2 to 3. So that's between 8 and 12. So let's just say 10 hours a week. So now you're spending 10 hours a week during a 4-month semester. Now you're going to compress that into 4 weeks. Okay, so you're basically going to do 4 times the amount of work. So the numbers come out to be that you're going to be spending about 40 hours a week on this class. So you should be prepared for that. It's a full-time class. So when you think about 4 days a week, every one of these days is going to be 8 to 10 hours of effort. So be prepared that this is a full-time job. What I do is every day I show you exactly what the deliverable is. So when I say homework 8.1, that means you have gone in and done the exercises. You've read section 8.1, you've watched the videos for 8.1, and then you've done the homework, etc. Okay, so now here is the deadline. So what I decided to do to give you flexibility, since this is an online class, is the deadlines there's 2 per week. So you're going to have a deadline on every Wednesday at noon, which covers the deliverables that were covered on Monday and Tuesday. You don't want to fall behind. You're not going to be able to get up Wednesday morning and crank out all the information or all the activities for the Monday and Tuesday assignments. But I do want to give you some flexibility. So if you do get stuck Monday on something, you have time Tuesday morning to get help. If you get stuck on something on Tuesday, you have Wednesday morning to get help. And it gives you a little bit more flexibility since this is an online class. But Wednesday at noon is the first deliverable of the week. Then you have your Thursday and Friday activities, and these ones are going to be due the following Monday at noon. Okay, so if you look at these, down here I tell you when things are due. So Monday, everything's due, July 11th at noon. All your Tuesday activities are due July 11th at noon, Wednesday. If you look at your Thursday and Friday, they're due the following Monday at noon. Following Monday at noon. You go to the next week, exactly the same thing. Your Monday, Tuesday activities are due Wednesday at noon. Your Thursday, Friday activities are due the following Monday at noon. And you just go and you go and you go and you get to the end, the last week of the class, the full week on building this computer system. Okay, so it's very important to keep track of these deadlines and do not fall behind because there's too much work to get caught up. This is a different view of all the assignments. It shows it to you in like a table form, but it shows you the amount of points associated with it. And I did duplicate the deadlines here so you can see what's going on. But here's the 4 weeks of the class. And you'll notice that when you come over here, homework assignments are worth certain points, labs are worth certain points, quizzes are worth certain points. And you'll notice that the labs have a lot more weight to them. Okay, so these are 50 points for a lab on 8.1 versus a homework which is only worth 3. I also made a note on here which homework assignments are going to be VHDL simulations, and you'll notice that those are worth more points than the multiple choice quiz format homeworks. Okay, so you can actually walk through here and you can just, as you knock these off in Brightspace and you get graded, you'll be able to see your points just accumulate. Okay, and so you go all the way down here. Like I said, here's the totals for each of the categories. These add up to be 1,000 points. Okay. Then if you're curious about why we're doing this, everything we do in a college class is for something specific. We're trying to learn something specific. So I actually put down the specific learning outcome for every section that we're going to cover. And I give you a little bit of, Bloom, kind of Maslow's hierarchy here, or Bloom's taxonomy in terms of what level of learning you're doing. So there's low level learning like knowledge and comprehension where you're just like learning something, just getting facts and figures together. Then there's also pretty high level modes of learning where you're actually designing something. Okay, so I just call those out if you're curious why we're doing this. Okay, so that's the syllabus. Now let's take a look at what this course is going to look like when we get into the content. So if I click this arrow, I go over to Module 8. Every module has this same format. You're going to have the learning outcomes. That's what we're going to learn when we do these activities. And you're going to have activities broken out by the section. So in section 8.1, you're going to read the textbook, you're going to watch a video, and then you're going to do the homework. 8.2, same thing. Read in the textbook, watch multiple videos this time, and then do the homework. 8.3, guess what? Read, watch the videos, do the homework. Repeat, okay? But then as they go along, after you get through certain sections, you'll end up having a lab video or a lab assignment where then you'll actually say, okay, I've learned all this content, I've done the homework, now I'm ready to build some circuits. So what you're going to do is you're going to click on this lab description, and it's going to download this big lab manual. You only need to do this once. It's a big PDF, but you'll go through and you'll read the lab assignments in here, and you'll see what you're actually supposed to do in the deliverables. and then I do give you a video on all of them. And then when you do the lab, you're going to have these deliverables. So the videos and screenshots, you need a place to put them, so you're going to upload them to the assignment folder. Okay, so that's how this goes, and then each module has an end of module quiz. Okay, so when you click on these things, if you look at it, like when you click on one of these videos, it's going to take you out to YouTube. Now watch the sound here for a second. It's going to blast. Okay, I got the sound muted. But so it's going to have this video of me doing stuff like writing on paper or, you know, writing code or whatever. And so you just watch these videos on YouTube. If they're too slow for you, you can speed them up. You can do the settings to go a little bit quicker. And that's the videos. When you click on like the homework, what's going to happen is it's going to open up the quiz tool. Okay, so this first homework is a multiple choice quiz. So you come in here, and like I said, this looks a little bit different, but it'll come open, and it's just like a normal Brightspace quiz. So you come in here, and you're like, all right, here we go, quizzes. All right, when using a sensitivity list, what will cause the process to trigger? You enter your answer, you go down, you gotta make sure you can save and then wait until the deadline before you submit, or you can go ahead and submit it. It'll give you your grade immediately, and it'll enter into the grade book immediately. But the cool thing about it is that you could go to the quiz tool and actually look at these quizzes, and you can see all of them at once of where you are, but everything is linked in the content. Same thing when you have a VHDL design simulation. When you go to do the homework, it takes you to a web page, and it's going to define the problem for you, and it's going to give you anything you might need, like the functionality or the the test bench. And then it has a link to the assignment folder. So you click on the assignment folder, it'll take you to a place where you can upload your files. Okay, so that's a module. The good thing about it is that it's all designed where it's all the same look and feel. So you go to the next module, guess what? Learning activities are just the same thing. Read, watch a video, do the homework. Read, watch some videos, do the homework. Oh, and then it's time for a lab. Read the lab description, do the video, or do the assignment. And you just repeat and repeat and repeat. And you go through all these things, and then the course will be over. Now, you get to the last component of this course is this computer project. The computer project is the grand finale, right? So it's this huge amount of effort. It's going to bring everything together. So I have a pretty large, not necessarily too large, but I have a lot of videos to watch here, and I give you a project description of this, and this will be kind of the great moment of the class. Okay, that is it. So at this moment in time, you are prepared to start doing this course. So the first thing you're going to want to do after you watch this video, of course, and read through the syllabus is you're going to come out here and you're going to go to content, and you're going to go to module 8, and you're going to start by opening up your textbook, read section 8.1, watch the video, do the first homework, and repeat. Okay, good luck in this course, and I look forward to working with you.